Okay, good afternoon. So we will have the last session before the dinner tonight. And so this is an invited talk given by Stephen Galbraith. He's from University of Auckland, and he got his PhD in Oxford, and he's one of the leading experts in the world in elliptic cryptography and lattice. So please.
So I'd like to thank the organizers very much for inviting me to Japan. I always like to come here, and it's been a very nice conference so far. I enjoyed the sake last night, and I'm looking forward to the dinner tonight. So I have to be in the line of sight. Or that way, maybe? So I start with an apology. I don't really know very much about lattices. I don't know anything about post-quantum cryptography. I don't really know why you invited me, but I'm very thankful that you did. But at least I can give an outside perspective. So my talk is about challenges, and they're not challenges for me. They're challenges for everybody else, especially people who are interested in lattice cryptography and post-quantum cryptography. So I'm bringing some challenges for you to work on in the future. And that's PQ, that's for the French. I am an expert on lattices. So I like gardening. Right, so here's the plan of the talk. I'm going to talk a little bit about learning with errors and the short integer solution problem. I'm going to talk about how confused I am. I'm going to talk about some work on approximate common divisors that I've been doing, some comments about search decision reductions. And again, you're welcome to interrupt me at any time. The more questions you ask, we miss the bus for the meal. No, I promise I will finish on time, independent of how many questions you ask. All right, so we begin with learning with errors. So I'm now going to assault you with a complicated slide. There's a lot of information on the slide. It should shock you. You should be frightened, terrified, depressed by all this information. And this is just to specify learning with errors and the inhomogeneous short integer solution problem. Now, algebraically, what's going on is extremely simple. Learning with errors is here. It's a vector is a matrix times a vector plus another vector. That's learning with errors, right? It's just matrix times a vector plus vector. Algebraically, it's very simple. It couldn't be simpler. Well, actually, it can be simpler. It could be SIS, which is vector equals matrix times a vector. So from the point of view of algebra, which is my subject, it's very simple. But the complexity is all these parameters. There's an m and an n, which relate to the size of the matrix. There's a modulus q, and then there's some error distribution, which is where all the power and all the mystery is sitting. And usually this is going to be some Gaussian with some parameter, sigma, which is more or less the standard deviation. And my main comment, and I don't know how easy it is to see down here, but there's a lot of parameters going on in this system. There's a lot of parameters that need to be chosen, and the choices have a big effect on the security and practicality of the system. So a lot of you will have seen this in the summer school, I guess. You've probably seen a picture like this before as well, just to get things clear in your head. Learning with errors, you have a lot of samples of a kind of, would be an overdetermined system, but we added some error, whereas SIS, you've got a kind of underdetermined system, underdetermined system, and the important point is the solution you're looking for is small. This is some general remarks about LWE and short integer solution. So LWE, usually when people talk about LWE, they're talking about a situation where there's a very much most likely solution. You can't really say unique. You can say a solution whose probability that it's the solution is overwhelmingly higher than any other. And we think of that as a low density. This is language that comes from knapsack problems from way back in lattice cryptography. Low density means it's sort of one unique solution. And then SIS is usually considered in this high density case where there may be multiple solutions. Some of these are technical remarks. There's a standard fact that in LWE, you might as well assume the secret comes from the error distribution. That's a standard trick. And then once you've done that, once the secret is as small as the error, you can convert LWE to SIS by just concatenating them. So the LWE problem, AS plus E, can also be thought of as the SIS problem, matrix times vector. Right? So LWE and SIS are basically the same thing. Similarly, you can convert back just by diagonalizing. There's learning with rounding as well. I won't talk about that. And so this is a picture I stole from Vadim Lyubashevsky. All images in this talk are used without permission. And this is somehow the size of this, the error or the secret and the error together. So you start off with very small errors, and this is the difficulty, harder problems, easier problems. So you start off with very small secrets and errors, and LWE is easy, and then gradually it grows, and it gets harder and harder, and then at some sort of tipping point, you go beyond having a unique solution to having multiple solutions, at which point we might as well start calling it SIS or ISIS. I hesitate to use ISIS for obvious reasons. And then the number of solutions gets more and more, and the problem gets easier and easier because it's somehow easier to find one out of these solutions. So that's sort of a very rough sketch of what's going on with the LWE. Is any questions? Anyone got any concerns? Good. Okay, so lattices. Up to then, there's no lattices. It's just matrices, vectors. The algebra is very simple. How do lattices appear? Again, you probably saw this in the summer school. These problems are basically the closest vector problem in a lattice. So I'll just talk about LWE first, well, only. In LWE, you've got the sample B, and it's A times S plus an error. So what does that mean? It means that B is close to a lattice point, A times S modulo Q. So we construct this set here. This is a lattice. And you've got a sample B, which is close to some lattice point in L. So if you can find the lattice point close to B, then that lattice point will be of the form A times S for some S, and you've solved LWE. So LWE is solved by solving the closest vector problem, and conversely, somehow, the closest vector instance can be thought of as an LWE instance. Time for a joke. You want to know what the closest vector or closest lattice point is. There's a rabbit. The rabbit has to solve the closest lattice point problem. And I don't know if Dan and Tanya say, here's a joke for you, Dan and Tanya. Hey. Right. So, if you want to understand that LWE is a hard problem, you have to understand whether the closest vector problem is a hard problem. So, the biggest, most important challenge in lattice cryptography is to understand lattice reduction and how easy it is to solve the closest vector problem for instances coming from learning with errors. So to do that, you have to be an expert on lots of things. So how many people in this room, put up your hand if you're an expert in floating point LLL, enumeration, block size, Hermite factors, all that kind of stuff. I'm not even putting up my hand. I think Nicholas Gummer's here, isn't he? Yes, Nicholas Gummer is here. Anyone else putting up their hand? Okay, so there's one person in this room who has the confidence to timidly put up their hand. And I mean, it's about right. I mean, I would say in the whole world, there's maybe a dozen people who probably have earned the right to put up their hand to this question. I'm definitely not one of them. It's very complicated stuff, and not very many people understand this very well, which is a little bit of a problem for the rest of us, because we don't know. So here are some papers. Fong was here, but he's gone. Otherwise, there might have been two hands up. Rachel's here. Rachel's, hi, Rachel. You didn't put your hand up. Good. So this is certainly a challenge, is for more people to become expert in this stuff, I think. If we're going to have standards on these things, we need to make sure there are enough people who can. And the issue is not so much what can you do when you run a lattice reduction algorithm now. The challenge is to predict lattice reduction algorithms beyond the point where they're feasible. Right? It's easy enough to say, here's an instance, I can break it. What you want to say is, what does 80-bit security look like? What does 128-bit security look like? What lattice problem will take 2 to the 128 operations? We have to predict the running time of lattice reduction algorithms, which is a very hard problem, apparently. And progress has been made. I mean, there is work on this, but it seems very difficult. There are other algorithms to solve learning with errors and short-range solution. There's this Aurora Gay, not a big problem in practice. There's PKW, which asymptotically is probably something to be concerned about. It's often said that, well, it doesn't really matter because you need a very large number of samples. In principle, you need a large number of samples. You need a very large M. M was maybe I should go back to my picture. By the way, the slides will go online without all the images on them. Where did it go? Yeah, so the number of samples is this, right? So in LWE, this is M. M is the number of samples. So if you have a sub-exponentially long number of samples, you can run BKW. That's the idea. But that's actually not so much a problem because you can do this sample amplification. So even if you have a fixed number of LWE samples, it doesn't look like you could do BKW, but by taking small linear combinations of these things, you can somehow amplify your samples. And Lubishkevji shows this for LPM, but there's other papers that I've not written down that talk about this for LWE. And as far as I can understand, it seems to work okay. So the number of samples itself is not enough to stop BKW from working. So I think in the long run, BKW has to be considered when setting parameters, not only lattice algorithms, also BKW. These things, I'm only mentioning this because I did some work on it, but this is more for things like the Swift hash function. If you want to understand the Swift hash function, then you should look at my paper with Shibai, Liangxia Li, and Daniel Sheffield. If you're interested in this paper, then please send an email to Fong Nguyen, because this paper has been waiting for more than 12 months for a referee, and I'm getting a bit cross about it. And Fong, when I was beating him against the wall yesterday, he said, I can't find a referee. So if you want to read this paper, please email Fong Nguyen. Yeah, good. So what is important in LWE, at least from my very limited understanding? There's all these parameters, M, N, Q, sigma. What matters? So the number of samples doesn't seem to matter very much. In principle, the more samples, the more information, the more you can do. But like I said, you can do sample amplification. So you're not getting a lot more security by restraining the number of samples you release. So M you can pretty much forget about. Certainly this ratio sigma over Q. So this is the standard deviation of the errors. Q is the modulus. It's this ratio that's very important. And somehow, if it's too small, then you're in this, that's the left-hand thing in Lubishevsky's diagram. That's where that's getting easy because you're very close to a lattice point. So having a very small gap here is bad. This comes up in Regev's reduction. Regev says that this sigma should be, well, it should be asymptotically, it should be constant times Q. So this ratio should be constant according to Regev, and certainly bounded by, also lower bounded by square root n or something. So you shouldn't take sigma too small. On the other hand, you shouldn't take it too large either, because then you're going to the other side of Lubishevsky's diagram, to the right side, and it's starting to get easy again because there's starting to be lots of solutions. So this ratio is very important for the security. N's important because it's certainly for the BKW and for everything else, it's essentially determining your lattice dimension, your minimum lattice dimension. So the really important parameters are N and the relationship between Q, not the absolute value, the relationship sigma over Q. So the experts know this. I'm not saying anything original. This is something that not everybody agrees with Chris Pikert in this matter, but there's a good technique in arguments, which is the appeal to authority, and Chris Pikert is far more an authority than I. My final conclusion is that worst-case security reductions are really important in lattice cryptography, where there is so much rope to hang oneself with, by which he means lots of choices of parameters. And this came up from issues that arose from this soliloquy attack and small principal ideals and things that Dan worked on and so forth. And Chris's argument, which not everyone agrees with, is that that stuff doesn't really matter because if you follow the worst case results, you won't get these weak instances. That's Chris's point of view. And so what Chris would say if he was here, he's who you should have invited, he would say that the worst case reduction really does give you more security. You've got this bewildering array of parameters, and the guide, what you should use to navigate your way to make sure you don't make mistakes is you should use Regev's reduction or Pikert's reductions and whatever. These worst case reductions should be followed to stop you falling into dangerous territory. I'm going to come back to statements like this throughout my talk. So, how many people in this room, put up your hand if you're an expert at Regev's reduction to gap SVP, Fourier transform of Gaussian measures, and smoothing parameter? I'm not putting up my hand. Nicholas is very game. Okay, anyone else? Okay, good, excellent. Keita is into it. Yeah, so good. Oh, well, I'm very happy we've got a couple of hands. But again, this is very complicated stuff. There are very few people, I would say, that understand all the stuff very well. It's not easy. And I think there's more people that understand this than understand floating point LLL and all that kind of thing. But not very many. And there's relatively few. The intersection of those two small sets is very small. We're lucky we've got someone here. Next time for post-quantum, you get a Nicholas to give the talk. And again, so here's another challenge. We need more people to know what this is. What I would like to see is a kind of idiot guide to all this stuff, because I find I can't even read these papers. I just can't read them. There needs to be some kind of thing that even people like me can somehow understand how this stuff works. In particular, for choosing parameters. I think Chris Pikert and Daniela Michiencio and Ode Regev, I think they've made the idiot's guide, but they don't realize how much of an idiot people like me are, I think. Okay. Any comments or questions? No? Good. You're very obedient. You want to go to your dinner. So I've got some optional slides, but given the lack of questions, I can go through them. Modulus switching is very nice. This is something that came up in homomorphic encryption, but it's also useful in studying these problems. You take LWE, and I've unrolled the mod Q. So this is LWE, where I've explicitly said matrix times vector plus error vector plus some multiple of Q. And then you take Q prime, which could be anything else, any other number, bigger or smaller, but usually smaller. So multiply everything by Q prime over Q, and Q prime over Q, and then of course the Q prime over Q becomes Q prime here. And then you round this thing down, round its nearest integers, round the matrix to nearest integers, and then put the overflow into the E. And here I'm assuming that S is small. Yeah, S is a short vector. And you get this new instance, which is modulo Q. So Modulus switching is really nice. You take LWE mod Q to LWE mod Q prime. And you can do a similar thing for short integer solution. But from the point of view of the difficulty of the problem, note the ratio of the error term here, E prime, over Q prime, it's the same as E over Q, because E prime over Q prime, see? E prime over Q prime divided by the Q prime is the same as E over Q. And in fact, if anything, it's got worse. It's got worse because you've added in a bit of overflow. So that fundamental issue for security, the ratio between the standard deviation and the modulus size, it doesn't change under modulus switching. So, I mean, the experts know this, but it's something that entry people into the field should be aware of. don't think that you're going to make LWE easier by doing modulus switching. And same thing, dimension reduction. Dimension reduction just makes the modulus bigger, and it doesn't change the relationship. It again, makes it worse. So you can't make LWE easier by doing modulus switching or dimension reduction. The difficulty is somehow preserved through these operations. If anything, it gets worse. Again, another optional thing. This is just so I can advertise some more work. I think I will skip over this one. But anyway, there's this binary secret LWE. Nice. And then I once worked on this. OK, now things get interesting. Ring-LWE. Of course, nobody's using LWE. People want to use Ring-LWE or Entru or something like this. This is where all the efficient schemes are coming from. So Ring-LWE by Pikert, Regev, Lubashevsky, which is really kind of just Entru with a few extra twists. And I always feel sorry for Entru. I mean, Entru was created about 20 years ago, and it couldn't get accepted to crypto, and everyone was scathing about it. And nowadays, lattice cryptography is like the biggest thing, and it's basically Entru, isn't it? But the question is, do we understand the security of it well? I mean, Entru is still standing there. It hasn't been broken. There's been some tweaks to the way the parameters are chosen. So you could say it's been around for 20 years. 20 years, stable, it's ready to go. But on the other hand, this is just papers on ePrint in the last year that make some claim about Entru. Not all these papers are true. I'm not talking about signatures. Signatures, there were problems. Yeah. I'm talking about encryption. Yeah, thanks. There's some of these even in the last week or a couple of weeks, right? So with this one, this is friends of mine. Who was it again? Martin, Leo Ducaus, and I can't remember. Yeah, Chibai. That's right, Chibai. And then this is Junki Chun and some other people from Seoul. I mean, these are in the last couple of weeks, and it's kind of disturbing that there's still so much activity. So the question of whether these things are true or not, I'm putting aside. The question of what impact they actually have on security, I'm putting aside. But each of these papers has ideas in it, new ideas about Ring-LWE or Entru. They have new ideas which are being worked out as we speak, and their value or lack of value is being determined now. But my point is, this is a very unsatisfactory situation that even in the last few weeks, there are new ideas coming up about this area. I mean, this makes me feel very uneasy about it, because it only takes one idea that's right, and everything goes. So unlike LWE, unlike just the plain matrix version, which I didn't really talk about Regev's contributions, but Regev really tells you LWE is sound. He really says, if you can break LWE, you can break, worst case lattice problems. And he really gives very strong evidence that LWE is hard. We have, in principle, a similar argument for Ring-LWE, but it just says, if this wacky problem is hard, then some problem in wacky lattices is hard. It doesn't really have any meat to it. And the fact that there are new ideas coming up, to me, is unsettling. So in my opinion, we are not ready to be standardizing Ring-LWE or Entru. I mean, there's too many questions. That's my personal opinion. Anyone want to disagree with me on that? No, gosh. No. Okay. Next topic, common divisors. Oh, sorry, common divisors. So this is a topic I like very much. Whether it's important in practice, whether it's useful, I don't know, but it's number theory and I like it. This is also the most simple crypto system you could teach to your students, or to high school students, or to little children. Maybe, well, almost. Well, I mean, it's about as simple as the one-time pad. I mean, this really is a simple crypto system. The secret key is a prime, so I'm doing this as a symmetric version. The secret key is a prime, and to encrypt, you take some multiple of your prime, add some even noise, and add your message, which is a coin flip or something. And of course, to decrypt, you reduce modulo p, that kills off this, and you reduce modulo 2, it kills off this, and you get the message back. Wonderful, simple crypto system. And reduction mod p, I'm thinking of it centered around 0. So this E might be negative. And of course, this sort of appeared in various guises over the years, but was very much emerged as a homomorphic encryption scheme. I mean, I think it's hilarious, right? For decades, homomorphic encryption had been an open problem. It was that easy. I mean, what was I doing? I mean, and others in the audience who have been around a while, what were we doing? How did we not notice that? So I confirm again that I'm an idiot, and you should have invited one of these guys to be your speaker. Yeah. Okay, and this leads to a number. So where does the security come from? This leads to a nice computational number theory question. If you see lots of these things going by, think of this again as a symmetric system. You see lots of these things going by between Alice and Bob. They've got this shared key P. You'd like to learn P. So you have to learn P from all these shared things. And let's just call this error. Let's just call this whole thing E. So the approximate common divisor problem is, given lots of these samples, these noisy multiples of P, to compute P. And so this is, unlike learning with errors, this is not linked to any other problems in number theory. This is just a new problem that came up in 2009. Well, actually, it came up earlier with Galbraith-Graham, and then became somehow more interesting with the homomorphic encryption paper. So I've always found this a very attractive problem to think about. So that's the problem. Given all these multiples, find P. And straight away in the original paper, there are these very nice lattice attacks. And the best of them uses an orthogonal lattice. They have 2 orthogonal lattice attacks in the paper. And one of them is a bit strange, and then one of them is somehow more simple. And then there's also this paper by Ding and Tao. But in my opinion, the 2 methods are really exactly equivalent. But I'm happy to talk to you about that offline. And these lattice attacks are actually very good. They're very good attacks. In fact, approximate GCD, you should really think of as an easy problem. It's actually easy to solve the approximate GCD problem. It's so easy that the only way to get a good crypto system out of it is to take unbelievably huge numbers. Huge, huge numbers. Would you agree with me, Mehdi, that they have to be huge numbers? Mehdi knows more about this than I do. The numbers are huge. And they're huge because the lattice attack is actually pretty good. So yeah, this is some statement about dimension. Now, I was also interested because there was this, even the original Galbraith-Graham paper presented some kind of multivariate polynomial attack on the system. And also, it was mentioned in this paper. And then Cohen-Henniger also presented this, developed this method some more. And I was always very intrigued and confused about the relationship between this algorithm and the orthogonal lattice methods. So I had a student, Shishe Gebre-Yorgis, and somehow we spent quite some time trying to figure out what's going on with all this stuff. And our conclusion is that actually this method is never better than the orthogonal lattice method. So it's not quite a rigorous statement, but we have pretty strong evidence that the best attack is really this orthogonal lattice method, this method, and the Ding-Tao method are definitely better than this method. Now, you already said that in your paper too. So that's all. And this paper is also joint with Murphy. Sean Murphy's here somewhere, hiding at the back. Hi, Sean. And there's also some other things in our paper. We talk about some sample amplification for approximate GCD, and we talk about some kind of BKW type paper. And our paper's not an e-print yet, but it should be. So why am I telling you about this? Partly because I just like number theory and algorithms and lattice algorithms and multivariate algorithms. This is, when I say multivariate, I mean coppersmith method type stuff. But there's another reason why I want to talk about this problem. There's two reasons why I want to. This is very much why I want to talk about this. This paper, everybody should read this paper. It is one of my favorite papers in lattice cryptography, completely ever. It's not very easy to read, but what it does is it gives a reduction from approximate common divisor to LWE. So it really says, I mean, before that, we just had a problem. Approximate common divisor and some algorithms. And you would say, well, if I choose these parameters, this algorithm doesn't work. But what they do in their paper is they say, they give a reduction that says, if you can solve approximate GCD, then you can solve LWE. But Regev's told us that LWE is hard. So they really give evidence, proper evidence, that approximate common divisor is a hard problem. And they give a more efficient homomorphic encryption scheme. And what I really like about this is because they have a theorem that tells you if you generate approximate GCD in this way, it should be hard because LWE is hard. And if you generate the parameters according to the way this theorem works, this theorem tells you how to generate parameters. If you do that, it's much better against the lattice attacks. The numbers don't have to be as big. Basically, the errors have become, so if approximate GCD, normally in approximate GCD, P is big, Q is really big, and E is really small. But in their case, P is big, E is also quite big. E gets not so far away from P, and then the Qs don't need to be as big, and it's much more resistant to lattice attacks. So it's really interesting that the reduction really leads to better parameters, more security, a more efficient scheme. So this comes back to my moral. Again, I'm echoing Chris Pikett's words. The existence of this reduction really does give you a more secure system. It gives you better parameters, a better secure system. And that's why I like this paper. And the good project, which I can't get a student to work on, is to somehow really work out what the parameters should be and see if these parameters are useful for anything. Even comparing the homomorphic encryption with one of the other ones. Right, so yeah, this paper, I like it. That was one reason I wanted to mention approximate GCD, because I want to advertise this paper. The other reason is because I want to talk about adaptive attacks. So we know that in practice, things that behave like decryption oracles can come out of the way that some system is configured. Not necessarily because someone is decrypting for you, but because of some error messages or timing attacks or I don't know what. So we do have to be, we do have to be careful about having some kind of security when an attacker has access to a decryption oracle. So let's think about this basic approximate common divisor scheme. Remember that decryption is just reduction mod P, reduction mod 2. That's what the decryption algorithm does. So suppose you have access to a decryption algorithm and you'd like to learn the secret. Well, all you do is you query even integers whose size is about, you have some idea of how big everything is, right? Whose size is about P over 2. If your even integer is less than P over 2, then reduction mod P does nothing, and reduction mod 2 answers 0. And if your number is bigger than P over 2, then reduction mod P subtracts P. P is odd, so the bit is 1. So your decryption oracle immediately gives you a binary search on P, and you can clearly learn P in some polynomial number of queries. So this is a very simple way of demonstrating that the decryption oracle might really allow you to recover, not just, I'm not breaking a message here, I'm recovering the secret key, right? Recovering the private key from some decryption oracle queries. There's lots of, this is just the simplest way to explain it. There's lots of much more sophisticated ways of explaining this. In the original Van Dyck, Gentry-Halevi, Vaikuntanathan paper, there's a much more elaborate algorithm that achieves the same thing while making sure that the Cs are always well-formed ciphertexts, for example. So an open problem. This problem comes with a health warning. I don't advise you to work on this problem. I've spent far too many years thinking about this problem, and it has stopped me from doing other good research. This is a problem that I'm hesitant to give to any student because they will probably make no progress on it. I think this is very hard. Okay, and similar attacks apply to pretty much everything. Any homomorphic encryption scheme based on LWE, Ring-LWE, whatever, there are very similar, very easy such attacks. Except one scheme which is specifically designed not to be vulnerable. This is a paper by Loftus, May, Smart, and Vercauteren. They really given in CCA1. Yeah, so why am I talking about CCA1? I'm talking about using a decryption oracle to recover the private key, right? There's no challenge ciphertext here. You've got access to a decryption oracle, you make some decryption queries, you learn the private key. If at any point a challenge ciphertext comes, you've got the private key, right? So that's CCA1. So there's this paper by Loftus et al. That talks about that. Also, these kind of ideas work on all the basic sort of textbook encryption schemes, Regev scheme, and so forth. But of course, they're prevented by using padding schemes or more elaborate ways of doing it. So I mean, it's clear that you can turn an in-CPA scheme into a CCA secure scheme by some kind of padding scheme. But I did want to say that also these sort of issues come up in the side channel attacks world as well, because side channels and decryption oracles are somehow a little bit related. So this is sort of an area that needs to be thought about, and I don't think, I mean, again, people know about this, but there hasn't been a lot of work done in this kind of area. And that's an issue, isn't it? Lucky it wasn't a tissue. That would be back to PQ. Right, but here's a bigger lesson I want to tell you about. And this is something that I'm trying to get around to writing up. There's these very nice, anyone who's studied LWE knows, there's this very nice search to decision result. This is in Regev's original work, and it shows that if you've got an algorithm for the decisional problem, so the decisional problem tells you, is this a sample from the LWE distribution, or is it a uniform sample? And so distinguishing genuine LWE samples from uniform, that's the distinguishing problem, or the decisional problem. And the computational problem is computing the secret. So what there is there's these reductions that say, if you can solve the decisional problem, then you can solve the search problem. This is, from a theoretical point of view, this is really nice. And it's very important in the security proof because it transforms a decisional, I mean, you're playing an end game, right? So an end game is a decisional game. Is it an encryption of M0 or an encryption of M1? You've got an adversary who's solving a decisional problem, and you want to show that if that adversary exists, you can solve some computational problem. So you want to amplify decision to search in the security proof. So that's how it comes in. You want to turn your decisional adversary into a computational adversary. So the search to decision thing is I mean, it's important, it's great, it's fantastic that it exists. But there's a dark side. There's a dark side to this. So the cryptosystem designer, someone very clever like Regev, he tells you, if you've got a decision oracle, here's how you solve search problems. So Regev's done all this work for us. But he's become a cryptanalyst at this point, because if you give me access to a decryption oracle, I can turn a decryption oracle into a decision oracle, essentially by creating a ciphertext out of the sample. And if the sample is an LWE sample, I've got a valid ciphertext, and I'll get the message back. And if the sample is uniform, and I decrypt, I have only 50% chance of getting the same bit back. So a decryption oracle, there's some details to be checked. But essentially, a decryption oracle is a distinguisher for the LWE problem. And Regev has told us how to use a decision oracle to solve the search problem. So Regev's reduction combined with a decryption oracle gives us an algorithm to compute the private key. So anytime you've got a search to decision reduction, you've got an adaptive attack on the private key. That'll be a theorem once I've checked all the details. So the moral of the story is, worst case security theorems lead to less security in this case. So what that means for the thesis of my talk, I don't know. Well, it probably means you should use a padding scheme, and then what I've said doesn't work anymore. But homomorphic encryption is still a problem. Side channels, there's stuff on side channels. There's this paper by Fan and Vercauteren. There's a talk tomorrow about preventing side channel attacks for Ring-LWE. So that's very active. So at some point, I thought to myself, it's these search to decision reductions that are the problem. We should find some case that doesn't have a search to decision reduction. And I remembered that it's actually an open problem to prove search to decision for general rings. So it's still an open problem. For Ring-LWE, there's a search to decision reduction, but it needs Galois number field and a completely split prime and some bits like this. And so for general rings, there isn't some reduction known. So I thought, this is good. For these rings, there's no search to decision reduction, so probably you can avoid this problem. But it's really the worst of all worlds. You don't have enough, somehow, mathematical gadgets to prove the strong theorem, but there are enough mathematical gadgets to still break the security. So in that case, you still get the adaptive attack without even the search to decision. So that's, again, something that I'm trying to write up. So it's pretty annoying. OK. And then, so the other thing I thought about is whether you really need to separate the assumptions. So this is a little moral of the story from ancient times. Let's compare RSA and Rabin. In RSA, computing the RSA private key is the factoring problem. If you can compute the RSA private key, you can factor. Whereas breaking a ciphertext, breaking the semantic security problem, is protected by the eth-roots problem, the RSA problem. So for RSA, the problem that breaks the private key is different to the problem that breaks messages. And this leads you to this question of, does a decryption oracle allow you to factor? No, as far as we know, a decryption oracle doesn't allow you to factor. And there are these two wonderful conflicting papers in the literature, one that says breaking RSA is not equivalent to factoring, and one that says breaking RSA is equivalent to factoring, and nobody knows the answer. But the point is that these two properties, computing the private key and the semantic security assumption, are separated in that case. The Rabin cryptosystem, that's squaring modulo n, doesn't have that property. The great thing about Rabin, supposedly, is that the semantic security depends on factoring. But then the downside was that if you have a decryption oracle, you can factor. Again, ignoring padding schemes for the moment. And I think it's very revealing that Rabin was basically never used. Basically never been used because it has this problem that if you get a decryption oracle, you can factor. And even though it's always been more efficient than RSA, it's basically never been used in all that time, since 1979 when it was invented. And so occasionally when I talk to Lattice people, they say, oh, this adaptive security stuff, it doesn't really matter. Well, I think the history of cryptography tells you that it actually does matter. And that people in the real world are concerned about the fact that some decryption oracle might somehow come out of some protocol behavior, and you really don't want to be learning your secret key in that way.
I would disagree.
Excellent.
It was there first.
1976 to 1979 or something. It's 3 years difference, you think? Yeah, but Rabin is almost the same time, right? It's a couple of years later.
Yeah, but it didn't get
Okay. Didn't get in Scientific American. Okay, you win. Yeah. Yeah, it's all Martin Gardner's fault. Yeah. Excellent. Well, we've generated some small controversy. Okay, I'm getting along with time. Further challenges. Okay, so I just wanted to say a couple of things about signatures very quickly. There are two general principles in cryptography for signatures: hash and sign or fiat-shamir. So again, taking standard examples, RSA signatures, as we teach them to undergraduates, is hash and sign. And fiat-shamir, as we sometimes teach to undergraduates, that's your Schnorr signatures, ECDSA, and so forth. And both versions exist for lattices. There's the GPV and lots of other papers doing hash and sign. And then there's the fiat-shamir, which is done by Lubashevsky and many co-authors and other people as well. And they're both good, but I think from my point of view, Lubashevsky seems to have the edge on performance. So that's good. And some of the early signature schemes, as were alluded to earlier, had some weaknesses. And there's this wonderful idea that comes out of Lubashevsky's work is this ensuring that the distribution, the output distribution of the signing algorithm is a fixed distribution that doesn't depend on the secret key. And this is using rejection sampling, and this is really great. It prevents these attacks. And again, so I'm going back to my theme again. The fact that you've got a nice security proof, you're proving that the signatures are not, the output distribution is independent of the secret. That proves that these kind of learning algorithms cannot possibly work because there is no information in the statistics to give a learning algorithm. So again, this is supporting the idea that security proofs are a good thing, and this is somehow why there was a rocky road for lattice signatures for a long, long time, and then now there's quite a smooth road because we have the right theoretical tool to understand the security. So I'm using this as evidence for the importance of security proofs. I never thought I would give such a talk, but there you go. But I've got some open questions because I think these are interesting. There's a gap between being so weak that you can be learned and being so perfect that there's no statistical information left. And I think it's an interesting problem to investigate the space between those two extremes, because the way you end up, when you're using rejection sampling, you end up having to hide your signatures with a rather broad distribution, and this makes your signatures quite big. So I think it should be possible to get shorter signatures by relaxing that statistical condition. And the other open question, again, this is well known, these Fiat-Shamir signatures, they're nice, but they're not actually a proof of knowledge. You have a proof that says if you can forge signatures, you can solve some problem. Not actually a proof of a specific solution. And this seems to be a really annoying problem that we don't know how to prove knowledge of us. So for LWE, you don't really prove that you know an LWE secret. You just prove you can solve some other version of LWE of slightly different parameters. Really annoying problem. Right, so my final slide. What have we learned from this, apart from being slightly closer to dinner? I think we need more people who know about all the aspects of this lattice world. It's not easy. There's a lot to learn about algorithms and mathematics. But I think it's necessary to get more people who really, really understand these aspects very well. Also in the Ring-LWE case, and that includes people who know algebraic number theory. And what's slightly worrying is that the payback's not necessarily, it's not clear what the I mean, you can spend your whole PhD reading and learning and studying all these other works, and then it's not quite clear what you would do. So it's actually, I'm not recommending that everyone start doing their PhD on learning everything in the subject, because you obviously have to solve problems as well. So anyway, but that's somehow a challenge for the community to get knowledge, and of course having a winter school is a good idea. I think people should start trying to do more about these adaptive attacks, especially in the case of homomorphic encryption. It'd be nice to make lattice signatures more compact. And then my final lesson for the congregation, when it comes to standardizations, I think people should not be too greedy. In my opinion, and I'm just a number theorist, in my opinion, post-quantum cryptography should be about providing greater security. I like elliptic curves, I love elliptic curves, but there may come a time when elliptic curves are not what you should use. You want to replace them with something that's more secure, not necessarily faster, not necessarily with shorter public keys. So I'm prepared for industry to take a hit on efficiency rather than security. Okay, that's my talk. Thank you very much.
Okay, any question? Yes.
Just another comment about the Rabin example. There was actually a pretty usable email encryption program called RPEM from Mark Riordan, and the RSA company shut it down using their patent. It wasn't totally clear that Rabin was covered by the patent, which was also why they were quite eager to shut any Rabin implementations down. Rather than RSA, they were tolerating some RSA implementations that they were in control of, which their patent was clearly controlling.
All right, thanks. Yeah, I didn't know that, so thanks, Dan.
Any other question? Okay, maybe I'll ask. Oh, there's one, sorry.
In lattice theory, the ideal lattice is more efficient than lattice, than integer lattice, and the Ring-LWE is more efficient than LWE. I want to know why.
Oh, I think it's more efficient because there's more structure. I mean, there's more structure, so it's more efficient, but also that leads to security questions, and that's really what my final comment is coming down here. I think I would be pretty comfortable with using LWE because we've got Regev's theorem, and I mean, there's really strong evidence to think that LWE is secure. Modulo those problems about exactly how you choose parameters that we don't actually know, but you know, in some sense, that is the only issue to work out. Whereas with Ring-LWE, we just don't know, and I don't think the fact that doing it with LWE is, you know, 2 or 3 times slower should be the deciding factor, right? 2 or 3 times slower is fine if it's a lot more secure.
Actually, it's more about bandwidth, not speed.
Bandwidth, well, yeah, that may be an issue. I don't know anything about the real world. All I know is people watch movies on their phone these days. They watch movies on their phone, so I don't know.
Okay, I wanted to make one remark. You were talking about the connection between security proofs on the one side and security of crypto systems on the other side. It would be very nice to have security reductions which were explicit in the sense that you can when you aim or when you target at a specific security level, you can select the underlying problem instance that provides such kind of security, and from this you could deduce the parameters. And I think most of the security reductions do not allow you to do this. And then also, when you use the worst to average case reduction and you apply the strategy, the parameters become so incredibly large that the schemes are totally inefficient. So the goal should be to get the gap between the real security on the one side, security level, and the hardness closer.
Yeah, no, I exactly agree. That's in some sense what I meant by that challenge about we want tools. I mean, really tools that allow to do this for us, to trace through the tightness and the aspects of the reductions. And yeah, you want to close that gap. I mean, the thing I skipped over about the binary LWE was exactly trying to close the parameter gap between practical cryptanalysis and the theoretical bounds. And yeah, I absolutely agree. I mean, and this is not some minor little, oh, someone should go and do that. I mean, that's really a research program that's going to take years of work by people who really know what they're doing. It's not easy. No, not always appreciated. It won't get to crypto paper, right?
I just want to confirm that about the result of the zero knowledge proof by Lubaszewski. If I'm not mistaken, it should be he reduced to the security of the SVP instead of LWE or SIS. So I just want to ask, what make you feel annoying about this result?
So Lubaszewski's papers on signatures, most of them have a theorem that says something like, if there's an adversary, if there's a forger for the signature scheme, then there exists an algorithm that solves LWE with some parameters, or an algorithm that solves SIS with some parameters. So that's the way the theorems are stated. And you have several game hops, and one of the game hops an adversary with an advantage there is solving LWE, and another one of the game hops, an
Okay,
adversary
so
is
it's
solving
all-
SAS.
okay.
So they're really, the proofs are quite complicated. And that's what I mean that they're not a proof of knowledge, because, and also
Yeah.
the parameters, the LWE instance that this game hop is solving is not with exactly the same parameters as the
Okay.
public key, and the SIS thing also is not the same. So, I mean, you know, it all works, and it's fine, and you can get good signatures, but it's pretty far
Okay.
from being a proof of knowledge.
Okay, I understand. Thank you very much.
Any other question? Okay, I have just simple question now. So you claim that we should do reduction, and then we should use the reduction to select parameters, right? But when you do reduction, and you reduce to a lattice problem, and I think we have also a lack of knowledge about how hard it is to solve those mathematical problems, right? I mean, in terms of, LL is doing much better practically than theoretically. How about this problem? How do we deal with this problem?
Oh yeah, exactly. I think that was my first challenge, right? To predict lattice reduction algorithms and to understand BKZ and all that. I mean, that was my first challenge, I think, was exactly to understand the cryptanalysis of lattices.
Yeah, but this problem has been existing for a long, long time, right? So we didn't do much in terms of how understand the problem, understand why there's a gap. As far as I know, there's nothing new, right? In the last whatever.
No, I mean, there's been some good papers like the LLL on average paper and predicting lattice reduction.
But those are mostly experiment-based, no?
Well, they have a mixture.
No,
of
you like reduction,
theory,
you like a proof, right? But there's not much proof to experiment.
I think these are hard problems, right? These are really
Yes.
hard problems. Yeah.
No, what I say is we haven't done much on this. Do you agree? I mean, in terms of theoretically understanding what is going on.
Yeah, I think there's a lot more to do. Absolutely, yeah.
Okay.
But I don't want to. I mean, I think a small number of people have tried. I mean, it's not because someone was lazy, right? I mean, I think these are actually hard problems, and Fong and Nicholas and
yes, they did great work.
Damien have really worked on this
yes,
stuff.
Yes,
and,
yes.
But
but
we have what we have, right? But more is needed.
But from what I know, most of the work is done in a way, it's empirical data-based knowledge.
This be empirical. A bit of theory as well, I'd say.
Not so much as I know. I mean, from what I would think that would be a very important problem in the sense, if we have a knowledge gap there, and we are worried someday we fill the gap, then the reduction algorithm may become much better. Then we're in trouble.
Yeah, I agree.
Yeah. Okay. Any other question? So if not, let's thank the speaker again. Okay. Thank you.